Okay, now let's continue from where we took off. We were talking about why power electronics so that we can see some of the motivations behind the idea of bringing in power electronics into electrical engineering. But then, in the first video or in the previous video, we were talking about how to convert voltage from one level to the other. But bear in mind, we were dealing with only DC. So we are going to look at some of the circuits that we can just use these power electronic switches that we've already mentioned about to design. So we will look at how they are also helpful in the electronic world or in the electrical engineering field. So in here we have few converters. We have a rectifier which converts AC voltage to the corresponding DC component. We have an inverter which converts electrical energy from DC to an AC component. We have a chopper. The chopper changes the DC from one level to the other. So it only works with DC systems, whereby we change it from one level to the other. Just as we've already done in the previous video, we change from 12 volt DC to 8 volt DC. So they are all type of choppers. Then we have a cycloconverter. A cycloconverter actually changes the voltage levels of what? An AC system. And at the same time, it changes the frequency of the system too, or the source. Now, the final one that we'll be tackling is a regulator. So, the regulators are used to maintain some actual values of voltages at the end of the circuit that is being designed. So, these are some of the converters. So, after we've known those, we just want to look at how they are still useful in the power electronic world. So we are still reviewing why we should employ power electronics in electrical engineering. Now, let's come to how a transformer works, or what are some of the requirements of a transformer working effectively or efficiently. We all establish the fact in machines that before a transformer can give us the highest efficiency or the optimal efficiency, this condition has to be met. You see that iron loss should always be equal to copper loss before we can have maximum efficiency. But then, what is the meaning of copper loss? Copper loss that we have here is just I square R. So we know that I square R is pertaining to the load that is being connected to the transformer. So if the load side changes, or if the current of the load or the resistance of the load changes, then it will affect the copper loss. So it tells us that we have no control of the copper loss. There's no way we will be able to maintain this value so that it can always be equal to a constant value of this. So the only way that we can maintain this kind of condition is that though the copper loss is not constant, we can still vary the iron loss so that it will always match the copper loss. So how do we achieve that? Definitely, we should be able to know the conditions that come together to give us our iron loss. So now, we all know that iron loss is always proportional to the voltage and the frequency. So, and the inverse of the frequency. So, if I'm able to change the voltage and the frequency, I'll be able to change the iron loss. So, what we do is that we can employ any of these converters, which is the cycloconverter. You can use the cycloconverter to change our voltage, and at the same time, we can use it to change the frequency. So, by doing this, we should be able to match with the copper loss at all points so that this condition can be met in the industry so that we can get our maximum efficiency from the transformer. So this is another point that will establish that power electronic is very, very, very important in the electrical engineering field. So we'll meet in the next